let's find the fourth degree polynomial approximation for e to the x about 0. So c, actually I need to change this a to stay with the notation we've been using. So a equals 0. Okay, so let's start off with looking for some derivatives. The 0th derivative evaluated at a, which in this case is 0, is equal to e to the 0, which equals 1. The first derivative evaluated at 0 equals, well, the first derivative of e to the x is in fact e to the x, so that's just going to be e to the 0, which equals 1. Now, this will actually continue on, well, forever. The nth derivative at 0 will always be e to the 0 equals 1, because the derivative of e to the x is always e to the x. So, well, that makes that easy. So, I'm going to expand this about a equals 0. So now it's going to look like 1 times x minus 0. So I'm just going to leave the, well, I'll write it in at first. Minus 0 raised to the 0 over 0 factorial plus 1 times x minus 0 to the first over 1 factorial plus 1 times x minus 0 squared over 2 factorial plus 1 minus, whoops, got ahead of myself a little bit, 1 times x minus 0 cubed over 3 factorial plus 1 times x minus 0 to the fourth over 4 factorial, which obviously I'm not going to leave it like that. This is going to be 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Now, just looking at this thing, I'm thinking in terms of trying to come up with writing this a slightly better way. And I can write this, I'm going to say that e to the x looks like it's equal to or approximately equal to the sum. N equals zero. Well, let's go ahead and change this real quickly. I'm going to make a jump on you here. I'm going to say that it actually equals, n equals 0 to infinity. This is actually e to the x of, I have x to the n over n factorial. Now this was the fourth degree approximation, and if I were to continue this out into infinity, I'd end up with this series right there, and that's an infinite series. And what I'm suggesting at this point is that this infinite series will actually be equal to e to the x. A little bit later we'll talk a little bit more in detail about how to show that this is actually true. But for right now, that seems like a logical sort of thing to assume. So what I want to do is I want to figure out what the radius of convergence is going to be on this. So if I take a look at the limit as n goes to infinity, absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. This is equal to the limit as n goes to infinity of absolute value of x over n plus 1, which equals 0. Therefore, this converges for all x. That's kind of nice to know. So here's my fourth degree polynomial approximation for e. And then if I keep going beyond that and go out to infinity, I get this infinite series, which I'm suggesting is in fact exactly equal to e to the x. And I now know that it converges for all x. Well, let's do this real quick. Let's jump to Maple. And let's just do a couple of quick graphs here and see what we got. What I want to do is I am going to plot let's start off with e to the x. And then I'm going to, oops, I need a bracket there. Then I'm going to put in there, let's see, what was my function again? My fourth degree right there, 1 plus x squared, okay. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And let's do x equals, I don't know, negative 10 to 10, and y equals negative 1. Let's just go out to 20, see what it looks like, and then obviously make some adjustments. Okay, what do we have? Let's make this bigger. Okay, we can see that's e to the x, and this is my fourth degree polynomial approximation. So actually, it looks like it's pretty good right away. If I go out farther, let's just go out and add a couple more terms. X to the 5th, oops, over 5 factorial, and, oh, let's take a look at that, because that's an odd polynomial. See what that does. See, now I have, obviously, there's my polynomial approximation. That's the odd polynomial. And you can see, gosh, you know what? It really does pretty good. But if I add yet another term, plus x to the 6th over 6 factorial. See, now it's getting tighter and tighter here. So I'm really starting to get a really, really good fitting here. And obviously, as I keep adding more and more terms, what will happen is this polynomial approximation, if it's even, like a 6th power, 8th power, 10th power, will start actually getting a little bit fatter and fatter and fatter, and will spread out more, and will match e to the x further into negative value for x. And although I stopped her at 20, you know, higher on the y values as x increases. Okay, based on that, let's go back to our screen here. Based on that, can we come up with an infinite series? Based on this series, can we come up with an infinite series for e to the x? And, well, yeah, actually, I got ahead of myself. I just did it right there. All right, so based on that previous infinite series, can I come up with an infinite series for e? Well, we said that e to the x equals the sum, and equals 0 to infinity, of x to the n over n factorial. And we said it converges for all x. So how can we modify this to become an infinite series for simply the value e? Well, isn't it true that e is equal to e to the first? So if I make x equal 1, that will give me that e to the first, or just e, is equal to the sum, and equals 0 to infinity of 1 over n factorial. Because we said it converged for all x, and 1 falls under the category of all x. Now, this brings us to the idea of the definition of the nth Taylor polynomials. Actually, this did right here. This is a fourth degree polynomial. It's a polynomial approximation as compared to an infinite series. Now, very commonly we'll see t used for a Taylor polynomial. We also sometimes see it for a partial sum, because a Taylor polynomial, t of n is a partial sum. T of n equals f of a, that's the 0th derivative, plus f prime of a, x minus a, the second derivative, x minus a squared over 2 factorial, all the way out to the nth derivative evaluated a times x minus a raised to the n over n factorial, which I can write as, well, let's just write it as Tn of x. the nth polynomial, Taylor polynomial, will be the sum I equals 1 to n, I'm stopping at n, hence the nth, of the ith derivative evaluated at a times x minus a to the I over I factorial. See, this describes what we're looking at right there. That actually describes that quite nicely. Now, the Maclaurin polynomial is actually nothing more than a special case of the Taylor polynomial. And with the Maclaurin polynomial, what happens is a equals 0. So whenever we have a situation where we expand about 0, we're doing a Taylor polynomial or Taylor series about 0. That's really all a Maclaurin series is. It expands about 0. Earlier we did one, well actually e to the x. This is, right here, this is actually a Maclaurin, L-A-U-R-I-N. It's a Maclaurin polynomial for e to the x. And sometimes you see the notation just p, Pn of x, the nth Maclaurin Taylor polynomial. I guess p is for polynomial. This is actually, because this is an infinite series, I'm expanding this about 0, this would actually be a, it's supposed to be an m, a Maclaurin series. A Taylor series will be expanded about a, and a Maclaurin series is expanded about 0. So the Maclaurin series, which I'm going to use Pn of x, Maclaurin polynomial, the nth Maclaurin polynomial, will be the sum I equals 1, oops, it should be 0. I had a 1 here. Let me correct that. 0 to n of the ith derivative evaluated at 0, x minus 0, so that's just x to the I over I factorial. This is a Maclaurin polynomial. And obviously, if I change that and let I go to infinity, and actually I'd write it as n equals 0 to infinity, then we'd have the Maclaurin series.